Let's take a look at an example problem from Module 10 for ME12 Dynamics course. So for this example problem, they give us a 3D diagram. In this 3D diagram, we can see we have two planes, two slopes right here that are at 45 degrees. And going across this, we have rod AB here with a wheel on either end of it, one at A and one at B. And they tell us the length of this rod is 10 meters. Now they also show us in the diagram that moving down this ramp on the left, we have velocity of A at 2 meters per second and acceleration of A at 3 meters per second squared. Now in our problem statement, they tell us that point A on this rod AB has an acceleration given to us as 3 meters per second squared, which we can see in our diagram, and a velocity of 2 meters per second at the instant the rod becomes horizontal. Now they ask us to find our angular acceleration, our alpha term, of the rod at this instant when the rod is horizontal. So our plan, we're going to follow our general problem solving methods in order to come up with a solution for this problem. So now that we've had a chance to read through that problem statement and take a look at the given diagram, the next thing that we want to do is create our setup page. So with our setup page, what I've done first is my hand drawing of our simplified diagram from the 3D diagram that they give us in the problem statement. So I draw this out. I draw out my two 45-degree ramps over here, and I have my rod AB going across it at a length of 10 meters. I have my VA and my AA, and I can tell that these are 45 degrees. And I pick my coordinate system to be positive x to the right and positive y going up. Now, the first thing that I notice is that there's going to be a lot of geometry and trig in order to solve this problem. So what I've decided to do is I realize that my handwriting is not the neatest, so I've decided to go into just PowerPoint and draw out my diagrams. So I redraw out this hand drawing up here of my initial given diagram in 2D down here to this neater version within PowerPoint shapes here. So again, I still have my rod AB going across from A to B, and I have these two angles down here, 45 degrees. I can tell this is my going down the left slope over here. A is my acceleration of A and my velocity of A, and I have my coordinate system over here and my length of the rod. So I have everything there. It's a little bit neater, and it's going to be a lot easier to break this down into individual parts as I start doing out some trig and geometry as I solve this problem. Now on the left over here, I also have the given that VA is equal to 2 meters per second, and my acceleration at A is equal to 3 meters per second squared, and my length of rod, which I'm going to call RB relative to A here, as 10 meters. And what I'm looking for is to solve for my alpha term. So with all that given information, I am now able to start my actual solution to the problem. So as I'd mentioned, I realized that there was going to be a lot of trig, geometry, drawing things out in diagrams. So I chose to type out my equations and to draw out my diagrams, again, all within PowerPoint here, just to make it a little bit neater and easier for myself and for everybody else to follow along with my work. So this is the case also as you're doing out your homeworks or exam problems. If you find yourself in a type of problem like this, where you're going to need a lot of extra space, and things are going to get complicated quickly with all these different angles and lengths and vectors, then potentially drawing it out by hand might not be the best option if you have messy handwriting like me. Maybe you want to use PowerPoint, maybe you want to do it in Microsoft Word, or even a SolidWorks sketch for some of the other ones. Or if you do want to do it by hand still, maybe just take up a little bit more space. Don't try to cram everything in one area. Make things a little bit bigger so we can see where all the individual components and values are. So that being said, I've now composed all of this within PowerPoint, so it's nice and neat for us to see. My governing equation I'm going to start with here is V is equal to omega R. So I can rearrange that. I know I need to solve for my omega term here, so I rearrange that. So my omega is equal to V over R for my general equation. Now, for my specific problem here, my omega, I'm going to start with AB here, is going to be my omega AB. So the whole length of this rod from A to B, right there, I'm looking for my omega term. So I can see down here in my kinetic diagram, there's my omega term down here that I'm looking for, rotating around from around point A, pivoting around point A. So this is going to be equal to my velocity at A, which is given in the problem statement, and my length here, r of A to my IC. So this makes me realize I'm going to need to draw out and find my IC. So I come over here to the right, under this diagram here, and I can draw this out. So I have my rod A, B, and what I can do here is I can draw up to where my IC is here. Now I know I'm coming off of here at 45 degrees. No, I'm coming off of here at 45 degrees. So that's at 45 degrees right there. This is at the center of my rod AB. Now I know the total length of my rod is 10. So at the center, that would make this half of my rod be 5. So from this here, it's just a little bit of simple trig. I have my angle, I have my adjacent, and I have my hypotenuse over here. So if I want to find this hypotenuse from A to my IC here, which I need for this equation over here, I can say, okay, the cosine of 45 is equal to my adjacent over my hypotenuse. Now I can plug in for that. My adjacent value is 5, and my hypotenuse is what I'm looking for here, r of A relative to my IC there, so this length from here to here. So the cosine of 45 is equal to 5 over my RA IC. I can rearrange that, solve for that length that I'm looking for here, and I say that my length from A to IC is equal to 5 divided by the cosine of 45. So now I can take this here, come back over here, and plug in right here, and that's exactly what I do. I plug into this relationship here for my 5 over the cosine of 45 on the denominator. My numerator is given to me in the problem statement. My V sub A is given to me as 2 meters per second. So I can plug those in, and when I solve that out, my omega AB is equal to 0.283 radians per second. So I add that down to my kinematic diagram down here. So for my solution, how did I do this? First step, so I solved for my angular velocity right there, and I located my IC for AB, which lies on the midpoint of our rod right there. So just a little summary of what we did in this portion of the solution. Now for the next part of our solution here, what I've done is I've brought over both those diagrams. So again, because I've done this in PowerPoint, yes, it did take me a little bit longer to draw these out initially than doing it by hand, but now I can cut and paste them onto different pages. So as I'm going through and solving this, I can reference back to them pretty quickly right on the same page. So I do this out. I have my initial diagram off on the left. I have my kinetic diagram over here on the right. I have my established chosen coordinate system, x positive to the right, y positive going up right here for both of these. And I have all my information I need, the length of my rod, my velocity at A, my acceleration at A. So the next thing I want to do is, since both points A and B are going to move along a straight line, so they're moving up the face of these right here, so these are two straight lines right there that those are moving on. So because of that, I can come up with these relationships down here by breaking my A sub A into its x and y components, and my A sub B into its x and y components there. So what I can do now here is I can say my A sub A, okay, I know my acceleration at A is 3, given to me as 3 meters per second squared. I'm going to break that down by the little trig triangle over here. If that's going down at 45 degrees, I can do out a little bit trig. And what I can say is, okay, my A sub A is equal to 3, magnitude of my acceleration, times this for my I components, my x values here, cosine of 45 I hat, minus the sine of 45 in the j hat, and that comes from my chosen coordinate system here. I can see A sub A is moving down into the right, so it's moving in the positive x direction and my negative y direction. So that's why I have a positive value for my x component and a negative value for my y component. Now I can do the same type of thing for A sub B. So I look at A sub B and I can say that's moving up this ramp here, so that's going in the positive x and the positive y, so both of my components are going to be positive here for my A sub B. So A sub B vector is equal to my magnitude of A sub B times the cosine of 45 I hat plus the sine of 45 j hat. Now both of these have units of meters per second squared. My next step in my solution here is to apply the relative acceleration equation. So as I apply my relative acceleration equation, pull out my general form for my relative acceleration equation right here, my vector A sub B is equal to A sub A plus alpha crossed with my position vector here, r sub b relative to a, minus omega squared times r sub b a vector here. So I realize there is going to be a cross product in here. I draw out my I, J, K triangle over here just so I can keep track of my sign convention as I do out my cross product. And I realize that these are all vector terms within there. So I'm going to need to really pay attention to my I and J components, my X and Y components for each of these as well. Now, I've chosen to bring over my values here for my equations for my acceleration sub A vector and my acceleration of B vector right there. And I have my values, and then right next to it I still leave the directions that those are moving in. So I start plugging in this fourth equation here, my A sub B relative acceleration equation here. So A sub B, the left-hand side, this is equal to this equation right here. So A sub B, as I said, A sub B times the cosine of 45 j I hat plus the sine of 45 j hat in meters per second squared. So I can plug that in here. A sub B is cosine of 45 I hat plus sine 45 j hat. And I've color coordinated my X and Y components, or my I and J unit vectors here with green and yellow. And we'll see why we do that in just a minute here. Now this is equal to my A sub A. So my A sub A I can pull from up top here. 3 times the cosine of 45 I hat minus the sine of 45 j hat. I plug that in right here for my A sub A. Plus now I have my alpha crossed with my r sub b a. So I look at this here. Well, my alpha is going to be in my k hat direction. And my r value here is going to have only an I hat, an x component. That's the length. It's 10 right there. So if I were to cross a k with an I, what do I get? So I go k crossed I get a j. So I write that down here. I'm going to have alpha times 10 in the j hat direction when I do out my cross product right there. And then over here I have my omega squared times my RBA. So I have my omega squared value that I've already found here. I'm going to square that times 10 in the I hat direction. So that's going to be in my x direction here. So you can see I color coded that green. So now I look at this here and I don't have an A sub B. And I don't have my alpha. Now, alpha is what they asked me to solve for in the problem statement. So what do I have is one equation, two unknowns. How do I get a second equation so that my number of equations match my number of unknowns? Well, the way that I do that is I break things down in terms of their I and J components, or their X and Y components. So now that I've color coordinated this, it makes life easy. So I just deal with my I hat components here. So I take everything in green from this above equation, from my relative acceleration equation here, and plug it in. So I hat direction, I have A sub B times the cosine of 45. A sub B times the cosine of 45 is equal to 3 times the cosine of 45 minus 2.283 squared times my 10. So this is all my I hat direction. So I look at this here. Now I have one equation, one unknown. AB is my only unknown there. So I can do the same thing for my Y direction, my J hat components here. I go through and this will be A sub B times sine of 45J is equal to a negative 3 times the sine of 45 right there. Plus, now I have my alpha times 10 for my cross product right there. And on this one here, I still have one equation, two unknowns. But for my equation above it, my x direction here, my I hat equation, this one right here, now what I can do is solve this one for AB directly. And when I do that, I get A sub B is equal to 1.87 meters per second squared. And I can plug that in right here. And then my only unknown in this equation is my alpha. And when I solve for that, my alpha is equal to 0.349 radians per second squared. And I write my little notation for the direction here, rotating counterclockwise.